So we, for example, transplant the process, synthesis process from other organisms, can be plant, can be animals, and this synthesis process would lead to a product of our interest. That can be flavonoid, can be other type of food ingredient or additive. And then instead of farming the trees or growing the animals, we use microbe to produce a specific ingredient in a bioreactor setup.
Welcome to the Science, Microbes and Health podcast from the International Scientific Association for Probiotics and Prebiotics. We're a non-profit scientific organisation also known as ISAP. I'm Marla Cunningham, ISAP's Executive Director. In our podcast, you'll hear about emerging topics across the fields of biotic substances and microbiome science. I hope you enjoy this episode with your hosts from the ISAP Board of Directors, Professor Eamon Quigley and Dr. Gabrielle Vinderola.
Hello everybody, my name is Eamon Quigley, and with my co-host Gabrielle Vinderola, we'd like to welcome you to this latest edition of the Science, Microbes and Health podcasts from ISAP. Our topic today is precision fermentation and useful fermentation end products. And we're really honored today to welcome all the way from Singapore, Professor Chen. William Chen is the Michael Pham Endowed Professor and Director of Food Science and Technology Program at Nanyang Technological University of Singapore. He is currently Director of Singapore Future Ready Food Safety Hub. The acronym is FRESH. He is also Director of Singapore Agri-Food Innovation Lab. That's a lot of work, Professor Chen. Tell us a little bit about your own background and what you're currently working on.
Hi, good morning, everyone. It's a true privilege to be here with the expert like yourself. My name is William Chen. I received my university education all the way from bachelor to PhD at the University Catholique de Louvain in Belgium. And that was mainly on the microbiology and the yeast genetic engineering. And after which I had done work on hepatitis B virus, surprisingly, before I moved into the food space. And for the past 10 years, Singapore government has been pushing all the effort in enhancing national food security. And therefore, we set up a capacity building program like the Food Science and Technology program at my university. We also push for food tech innovation to enhance current food system. And that include the valorization of food processing side streams, including soybean residue or brewer's spent grain. And one of the technology that we use is precisely fermentation. And this allows the breakdown of the polymeric form of the nutrient into monomeric form of the nutrient, including amino acid or fatty acid. And along the way, there is also a generation of these micronutrients in the form of vitamin, short-chain fatty acid from the microbe that we use in the fermentation. Alongside of this nutrient recovery through fermentation, we have also developed a technology platform to produce food additive or food ingredient through the process named as precision fermentation. And so our effort have demonstrated that food system can be enhanced through this reduction or valorization of food processing side streams. And the benefit is that the obvious benefit is that all these nutrients recovered from the fermentation process can be reconnect to the existing food system, which allows the reduction of the operating cost. And to expand this application spectrum, we have demonstrated that the nutrient recovered from our effort could also be used to replace the culture medium for the fermentation process, for example, therefore reducing the cost.
Thanks for being with us today. You know, ISAP has a long tradition in addressing fermented foods, but let's say traditional fermented foods. And in 2021, ISAP proposed a definition. And you're working in precision fermentation. How would you say, how imprecise is traditional fermentation and how it differs from what you do? How can we distinguish traditional to this kind of fermentation?
This is an excellent question. When we talk about fermentation, it's really a very broad terms In fact, we can separate roughly into 3 categories. I will say first one is a traditional fermentation. Second one is a biomass fermentation. The third one should be precision fermentation. By traditional fermentation, we meant to use natural microbe to alter the property of this food product or food ingredient. There are two direct benefits from this traditional fermentation. One is prolong the shelf life. Second one is this process give rise to different flavor and different quality of the food that has been fermented. Some example will be cheese and wine and some other more or less localized like Singapore in the Southeast Asia, tempeh, for example.
Right.
The second process is biomass fermentation. For this, we do not alter the microbe, but we use them to sort of the microbe itself themselves enrich in certain ingredient that could be protein, could be lipid. Then we grow them specifically to a large amount, so to get the final product enriched in a certain aspect of the property that can be lipid or can be protein. Some example can be a marmite from the yeast extract or mycoprotein for fungus. The last category is precision fermentation. Here, we actually use it as a car chassis, the micro. So we, for example, transplant the synthesis process from other organisms, can be plant, can be animals. And this synthesis process would lead to a product of our interest that can be flavonoid, can be other type of food ingredient or additive. And then instead of farming the trees or growing the animals, we use microbes to produce a specific ingredient in a bioreactor setup.
So I was fascinated by your review article. So there you spoke particularly about fungal food fermentations.
Mhm.
Is that a particularly productive approach?
I guess really at the proof of concept, there's no problem because basically you grow the fungus in the bioreactor. And the issue here is that there are hundreds of thousands of these natural species in the nature. So it's a matter of a selection. What do we want to produce? In the case of some commercially available product from this biomass fermentation, we're seeing corn, right? So that is unicellular fungus. The company has successfully grown and in a bioreactor setup and also marketed in various form of final product in the form of plant-based this and that. So the success rate is not limited to the lab scale. It has been, scale up to the commercial scale. So
Yeah.
I think this can be a sort of inspiration or motivation for other startups or small medium enterprise to follow the same path, but leading to different product. But there are so many different species.
So on a very simplistic level, could you just take me through the process whereby you take a medium or you take a substrate, you work with a particular microorganism, such as a fungus, and then you end up with the desired metabolite or molecule that you want. So how are you engineering the microorganism to produce what you desire?
So just now we're talking about the biomass fermentation. Now we are moving into the domain of precision fermentation. I use an example of what we have been doing. That is to develop next generation of natural food preservative. As we know, plants like animals, they also have their immune system, but in the form of flavonoid, functionalized flavonoid, or isoflavonoid. And these isoflavonoid or flavonoid molecules exist in a minute amount in all the plants. So they are activated when they are fighting off infection or infestation by pests or microbes. And therefore, the primary function of these molecules are antimicrobial. They also provide some certain antioxidant activity to protect the fruit plant from the environment, the damage from the environment. So we look at the pathway, synthesis pathway in the plant, and we realize that it's perfectly feasible, to transplant the whole synthesis process from plant to yeast, for example. And this is what we have successfully demonstrated that if the yeast can produce this natural food preservative in the form of functionalized isoflavonoid. And our activity assay has also shown that these yeast produced natural food preservatives are far more potent than the commercially available chemical preservatives. And they are both antimicrobial and antioxidant. And the good part is that we actually can minimize the skepticism about this natural molecule as being GM, a genetically modified ingredient, because the yeast, for some reason, they do not like this hydrophobic molecule because they will interact with their own plasma membrane or all kind of reason. So they will secrete this synthesized isoflavonoid out of the cells. So we could simply collect them from the culture medium. Therefore, we are not even touching the yeast. So they are still growing while we collect this substance in the culture medium. And there is a matter of concentrating and separating from the culture medium. Yeah.
So for this precision fermentation, you need to use genetically modified microorganisms. You cannot use like traditional ones. And what we heard from biotechnology is that, for example, E. coli or Lactococcus are the most easy to handle, to put some genes and to make expression. And you mentioned yeast. Are there already, these are the best microorganisms to use, or is just case by case?
This is a very sort of a scientific question. It's an excellent question. When we talk about the selection of the microbe to be used, we talk about prokaryotic and eukaryotic. Prokaryotic means bacteria, mostly bacteria like E. coli, lactobacillus that you mentioned. The yeast is actually a eukaryotic cell. The main difference between the two is the sort of modification, functional modification of the final product that the yeast had, like animal cell, like plant cell, but E. coli or bacteria may not have. And the other difference will be the capacity of production. The yeast is much bigger than bacteria. Yeah. So if the final product was to produce inside the cell, the yeast will have a bigger capacity. But in our case, it did not happen because the molecule that we want secreted out of the cell, which make our job a lot easier because we are not talking about GM. We just use it as a vehicle to produce, and then they come out of the cell. We don't even touch the cell.
Understood.
And are, are there already products in the market that you can say this is produced by precision fermentation? And if so, what are the costs compared to the traditional production of these flavonoids, for example?
In the food space, we have seen the soy leg hemoglobin that was used by the American plant-based meat company to sort of, this is a plant hemoglobin that from soybean, and the company used it to produce it through precision fermentation in a very similar way as our philosophy. We do not farm the plant to isolate the natural food preservative. Here is the same thing. They isolate this plant hemoglobin from the microbes, let them produce, and then incorporate them into the plant-based meat to enhance the color, the mouthfeel, all this kind of thing. And the other would be dairy protein. We talk about some of the ingredients that we find in the cow milk that have extremely higher value. And so these are already at a commercial scale, but how much they can be accepted by consumers, that's a separate story.
Right. What are the challenges with this approach? What are the limitations and what are the challenges?
Well, one is we cannot avoid the question or concern on the genetically modified aspect of this approach. Although we can sort of cut short the production time, and then also bypass the constraint of the space and land that needed to produce this, we ultimately have to address the concern of whether or not these are GM food, the ingredient. And for that, I guess one way is to really be transparent, right? We have to be transparent with the consumers. Labeling information have to be clear that you have certain ingredient, but to alleviate the concern or fear from consumers, I would suggest that we target on some of the ingredient that consumers are familiar with or have been used in the food industry. For example, in our case, the flavonoid has been used as additive in food products. So it's not something like the consumer had never been exposed to. So I think familiarity is a key factor to drive this commercialization of this precision fermentation.
Where do you see other opportunities beyond what you're working on at the moment, or even beyond food? Do you see other potential opportunities?
When we talk about precision fermentation, is actually synonymous to synthetic biology, metabolic engineering, and there is certainly, as you already suggested it, it's not limited to food. You can produce other high value chemicals that can be biofuel, long-chain fatty acid. But I think the key to the success of these all these endeavors lies on the cost factor. So if we talk about biofuel production, if we compete with a petrochemical, fossil fuel, I think there's a long way to go. But that doesn't mean that we should stop improving the process. For example, in the precision fermentation area, when we talk about the culture medium, that's one of the cost factors. What we have done is we have demonstrated that through our valorization of soybean residue, for example, we have demonstrated that the fermented solution from the soybean residue part of our effort can replace the culture medium of this precision fermentation because it's a microbe, the culture medium for microbe, at the fraction of the cost. We're talking about reduction of cost by 90%. And so there are ways to enhance or improve this urban solution type of processes, but it just takes longer time.
And I was thinking, okay, you are making a fermentation and you get a product, but you also get a lot of liters of culture medium. And what would you do with that? Is there any risk for the environment? Are you releasing genetically modified microbes to the environment? How do you deal with the spent culture media?
Ah, well, this has something on my mind for all the years effort that we've been doing in reducing food waste. Obviously, we do not want to generate a secondary organic waste, and then that defeat the purpose. There is this concept called circular process, through which we can use microalgae to use this medium to grow microalgae. Because microalgae is really robust, as long as you have, they don't really distinguish what is a consumed nutrient left behind or whatever. They just need sunlight and minimum nutrient requirement in the medium. And we have also demonstrated that microalgae can be grown on this culture medium. And in the process, microalgae can also be a source of replenishing the nutrient required for the microbe to grow. So you can see it's a synergy, symbiotic, and yet we can close the loop instead of disposing of this culture medium, large volume of this culture medium into the environment, which is absolutely not sustainable. Yeah.
That's great. And in at ISAB, we frequently discuss, in ISAB, we work a lot with probiotics. And probiotics, they had a very different regulation around the globe, and that's quite challenging. How do you see the regulatory landscape for precision fermentation product? Is there that you can produce here and sell anywhere, or you have to go country by country and see how they deal with the products?
This is quite challenging because every country's regulatory framework and approval process can be different. But I would say that this is an area that needs a concerted effort, not just from innovators, but also from consumers' help and then government's recognition of this importance of this precision fermentation product. So in our case, the natural food preservative from plants is at the end stage of getting approved by Singapore Food Agency, which is equivalent to US FDA or EFSA in Europe. I'm not sure in Argentina, the equivalent in Argentina. But I'm sure there's one agency dealing with all this approval process. And ultimately, we ought to look at there are two aspects in the approval process. First is at the ingredient itself. The second is at the final product, how much is being used in the final product. And so take the example of cultivated meat approval process. The ultimate concern that for regulators and for consumers is potential harm to the consumer health. And if we take the example of the ingredient we use, flavonoid from plant, which has been, they are plant-based product. So it's not like synthetic or anything. So the consumers have been exposed to these ingredients. The matter is, the critical part is whether these ingredients that we produce have been sort of contaminated by the yeast, by the producing microbe. If we can demonstrate that there's no yeast component whatsoever in the final product, I'm confident that this will alleviate the concern for any party. Yeah.
How would you communicate to people that this is coming from a genetically modified microorganism, but there is no microorganism there? How would you deal with consumer concerns?
Oh, I think education is key. Second one is transparency. Is the transparency in communication. Yeah. So the last thing we should do is that if let's say our natural food preservative, we put a little bit into the final product, but because the amount is so low that we do not say anything about it, then that is misleading. I think it's all about how we produce this, what is the process, what are the microbes used. In our case, it's a food grade, it's a grass microorganism, and a final product of nature's origin, and is sort of, and then we can demonstrate the superior functionality of this final product and the benefit of using this natural product in replacing chemical preservative. So it's really a judgment
An
call.
opportunity. Yeah.
Yes, exactly.
We're beginning to run out of time, but I have to ask you about one area of your work, which I think will be of interest to our audience, namely your work on producing low alcohol and alcohol-free alcoholic beverages, beer and wine. Tell us a little bit about how this technology can be used in the area of alcoholic beverages.
The microbe have been used in the past 100,000 years in producing alcohol. So there's not like any need for breakthrough in this space. In the process called anaerobic fermentation. So our focus is mainly to reduce food waste and then convert them into useful materials, be it nutrient recover, or it can be alcohol. But alcohol is just one of the options, not our main focus.
Absolutely. Well, we are running out of time. This has been a fascinating discussion. I would like to thank you for spending time with us. Glad to congratulate you on your wonderful work, and I know this will be of great interest to our audience. So thank you for being with us. It's been a great conversation.
Thank you.
Thank you so much, Professor. Thank you.
Thank you so much. It's a great honor.
Thanks for listening to this episode of the Science, Microbes and Health podcast from ISAP. Check the show notes for links and further information on this topic. You can also send us your feedback, questions, or topic suggestions by emailing info@isapscience.org. Don't forget to follow or subscribe to this podcast so you never miss a new episode.